Hi folks, Phil from statisticsmentor.com. Okay, I want to give you an introduction to implicit functions, and these are for economists. Okay, first of all, let me give you a few examples of what are known as implicit functions. X squared plus 2y squared equals to 3. Log of y plus 2x equals to 5. That's implicit. These two are implicit in two variables. Consider this one. Say this is implicit and it's got three variables, hasn't it? This one is not an implicit function, it's just an equation. It's a quadratic equation. So let's now write down what is meant by implicit equation. Implicit equation could be written something like this, and I'll do this case for two variables. Some function of our variables equals a constant. Now that constant could be 0. Why? Because if that's not a constant, if that's a constant which isn't 0, you could obviously take that to the other side, so it'll be left with 0. Don't want to make too much of that. Don't want to waste your brain thinking about that. In other words, if I'm looking at this, if I don't want a 3 there, I can take minus 3 on both sides, and that will be 0. 5 over there, 0. 1 over there, 0. Okay? So I'll just say that in case your lecturer presents it to you one of the two ways there. Okay? And this is for when you're doing it in the intro, as an intro kind of thing, you always just look at the two variables first. But and then the question is, where does this implicit equation appear in economics? Well, it can appear as a utility function or as a Cobb-Douglas type thing. So let's think about Cobb-Douglas type thing, that a input x to the alpha, y, beta, could be capital and labor, equals to some number. Alright, that's a function. Say, then that is Cobb-Douglas, a utility function. Let's see an example of that. Say a bundle x1 times a bundle of x2, so the half, say, given level of utility, say u1. Both of these are implicit because they both can be written of this form, with a number on the right hand side and all the variables on the left hand side. Okay, so that's two places where it appears in economics. What's the opposite of an implicit function is explicit. So when implicit basically means that all my variables are jumbled up together on the one side like spaghetti with a number on the other side. Explicit means I rewrite it so I get my thing of interest on one side and everything else on the other side. So for example, if I take that out, everything here is implicit. If I want to get this as an explicit for y, say I'm interested in y in terms of x, you just basically take the x squared, rearrange it so you get y by itself. So take x squared to the other side. So it's 3 minus x squared. Obviously you want to divide by 2. And then you want to take the square root of both sides. And that's plus and minus. When you take a square root, it's plus and minus. So here we have given you an example here where we have an implicit equation x and y. And then here we've got an explicit for y in terms of x. Okay, now I've told you what they are. The final thing, this is the big thing, is to find the derivative of an implicit function. So say, for example, I have this expression, x squared plus 3yx plus 2y equals to 48. Okay, and by the way, I've taken this from page 124 out of the main textbook in case you want to follow it. I'm going to show you I'm going to kind of go over the technique that you've learned in class, and then I'm going to show you what I consider as a faster way, which I never presented in class. Okay, well look, this thing, contour at 48, we've got axis x and y, and it looks something like this. And say I want the gradient at the point 4, 2. 4, 2, right? So I want to find dy, because it's y up here, but changing x, dx, at the point x is equal to 4 and y is equal to 2. That's what I want. How do I do it? Well, we can use the formula presented to you in the textbook, and this is, let's just rewrite it. This is the formula. dy by dx is equal to minus dg by dx, the partial, divided by dg by dy. And this is the formula that you memorize and apply. So let's do it for this case here. This one. This whole thing here on the left hand side is the g. Alright, so it's the gxy. G. So I want to differentiate this whole left hand side first with respect to x, the partial with respect to x. So what do I get? Okay, I get 2x plus 3y. 2x and then 3y. And then y, because y is treated as constant. Next, dg by dy. Look at this thing again. Now x is treated as constant, only y is the variable. So here we have 3x for the second term. And that's it. The first term is the first. No, third term also depends on y, so bring that down. Plus 4y. Okay, first term is nothing, it's a constant. So we've got these two things, now just put it into here. So therefore, our answer is that dy by dx is equal to minus. That minus is the whole lot, right? Some people get confused, whole lot, so let's put that in brackets. 2x plus 3y over 3x plus 4y. That's the expression. What you can see is that the gradient dy by dx changes with x and y, which makes sense because you can see in this picture here that the gradient is changing as you're moving coordinates, i.e. for changing values of x and y. Alright, so that makes sense. Finally then, at the point, we can answer the question at the point x is 4 and y is 2, we sub this into here, dy by dx, the gradient, which basically is there because it's a negative gradient, and put that number in there, get you out your calculator, minus whatever that number is, it's 7 over 10. Okay, two things to note. When you apply this formula, that minus sign, students get confused with that. That's not minus the first number here, so it's not minus 2x. It's not minus 2x, it's minus the whole lot, so hence I put the brackets there so there's absolutely no confusion. Do that if you don't know, if you think you're going to get confused. Second thing is, why curly d's instead of straight d's? Curly d's because you can see this function, implicit function g, is a function of more than one variable. Remember, when we do more than one variable, we use curly d's, meaning that this means that differentiate this function g with respect to x, holding everything else fixed. Now this method can be extended to a function of more than two variables, because here we have two variables x and y. We can do it for 3, 4, however many variables you like, and in homework you are asked to kind of think about just use this kind of pattern to kind of solve for the gradient when we have three variables. But at this stage I'd like to kind of present another way to do it, a way that you can do this without having to memorize this formula. And let's face it, we don't always like to memorize formulas, especially for things we don't use every day, or since we haven't used in the school days. So here is something you haven't probably not learned at school before. Say we get stuck, how can I solve this thing again without memorizing that formula? I can do it like this. So here is the second solution again, but doing it a different way. Okay, this is 48. So I just want the expression for dy by dx. Okay, the general expression. So I've shown you how to do it with a formula. Now here's the second method. I look at the derivative of both sides of this expression. So I do d by dx of the left hand side. And so I do d by dx on the right hand side. Obviously that is automatically 0. Derivative with respect to x of a constant is 0. So that's solved. So we need to look at this. Now this here method works well if you're comfortable with differentiate product rule, differentiation using the product rule, and the chain rule. That's all you need. But we're always using that in our course anyway, in economics. Okay, so the left hand side. Let's say left hand side. Okay, so it's just the sum, so we take d by dx right through. So this guy first, that's just 2x plus, now this guy here is a product of x and y, which is a function of x. Why it's a function of x? Because we're looking at y with respect to x. So here you could have written y in terms of x as an explicit function, right? So so we've got a product rule going on here, so let's put brackets here. Well, 3 is a constant, can come out. So we can first treat y as a constant, differentiate that with respect to x, so we have y plus, and then we write x and we differentiate y with respect to x, but as I said, y is a function of x, so we just write y, let's prime, let's say, to denote that's the derivative. So it makes it absolutely clear, because this way it could get stuck is here. Here y is a function of x, i.e. y x, yeah? If we want to write explicitly, the right hand side would be a function in terms of x. Right, and then finally the last term here, but y again, but that's y as a function of x. So I use a chain rule, so 2 down, that's 4y, and then I differentiate y with respect to x, so that's y dash. Okay, and that whole thing we just said on the right hand side is equal to 0. Now we just solve this. So let's gather together the y primes. You can see that that is what's that? That is 4y there. Therefore 4y. And then we've got a 3x here, 3x, and that is y prime. And then we take everything else to the other side. So we've got minus 2x. This guy go over there. Minus 3y, take that to the other side, minus 3y. And therefore, y prime is equal to minus 2x minus 3y all over 4y plus 3x. And isn't that the same as what we got previously? Yes. It's the same. Okay, so really this is a way that you could do it without knowing any formulas, and also this way you can easily extend it to any kind of function for any kind of number of variables. Here you've got 2, but you could do it for 3 like in homework, 4, blah blah blah, very easy. All you have to be comfortable about is the chain rule and the product rule. So to see whether you like this method, you might go back through the homework and just try doing this for some of the easy and the hard questions. But essentially that's it. So that's implicit functions. Implicit functions, then we see that we can counter those in economics, like in the Cobb-Douglas and utility function. Implicit functions are useful because sometimes it's very hard to write functions in explicit form, and it can also be a great big mess if we try to write it in explicit form. And then we've shown you how to find derivatives of functions, of implicit functions. Okay, well that's been helpful. Take care.